Let's go on to the property tables now and look at how to deal with things when we're in a superheated vapor region, right? We just looked at, as an example, tables A4 and A5, which are what we call the water saturation tables that deal with how to quantify the properties of water when it is in a saturated state for a saturated liquid, a saturated vapor, and a saturated liquid vapor mixture. Now, we're going to go beyond that state, and now we're going to deal with how to quantify the properties when we're in a superheated vapor region, right? So on the superheated vapor region, where we're looking at a T-nu or a P-nu diagram, right? The TV diagrams we were looking at earlier. This is the region to the right of the saturated vapor line, and at temperatures, above the boiling point here, above the above the vapor line there. So for water, that is table A6 in the back of your books. In this case, something to understand is that pressure and temperature are independent. They are not dependent. When you looked at the saturation saturation tables, if you know temperature, you automatically right away you also know pressure. If you know pressure, you automatically right away also know temperature. In this case, it is not true. In a superheated vapor region, pressure and temperature are independent. They're decoupled. You cannot just automatically know pressure because you know temperature, because they can be at varying values from each other. You are at a superheated vapor on all of these different areas, right? So if I sit here and go over all of these in too much detail, I might lose you because of the nature of a video lecture. But if you think about it, at a given temperature, if my pressure is less than saturation, I am at a superheated vapor region. At a given pressure, if my temperature is greater than saturation, I'm in a superheated vapor, right? So for example, at 1 atmosphere, if I have a temperature of 150 degrees Celsius, it would be superheated vapor because the boiling temperature is 100 degrees. If I'm higher than that, I am therefore steam or therefore water vapor, right? At a given pressure or temperature, if any of my specific properties are greater than that of the saturated vapor, I am a superheated vapor. All right, so let's look at a little example here of a superheated vapor, right? So table. So this is an example. This is an excerpt of table A6 from the back of your books. It's divided into regions. Okay, so here the tabulated values for temperature start at the saturation temperature that corresponding to a specific pressure. So here's a pressure, right? 0.1 megapascals. At that pressure, water boils at 99.61 degrees Celsius. So that's what this is, right? Saturation temperature. And then it increments it up to the nearest 100 or 150, right? So here's at 100 degrees, and then it increments temperatures, increasing in increments of 50 degrees. So for example, I'm at 100 degrees right here, right, which is a superheated vapor because at a pressure of 0.1 megapascals, water boils at 99.6 degrees. 100 is greater than 99.6, therefore I'm superheated vapor. And here's my specific volume, here's my internal energy, and here's my enthalpy, and you should also have entropy listed there. Those are all the superheated vapor property values for a temperature of, here for a temperature of 100 degrees Celsius at a pressure of 0.1 megapascals. Here are the properties for water or water vapor at 0.1 megapascals and 150 degrees Celsius, right? And then it's tabulated. Here's another section of the table where it's 0.5 megapascals. At 0.5 megapascals, water boils at 151.83 degrees. So it starts at that saturation and then it increments it up to 200. So at a pressure of 0.5 megapascals and a temperature of 200 degrees, these are the properties. What's great is that you can actually find out what state you are in. Well, I'll come back to that in a minute, actually. So this is a superheated vapor table. The last section that we're going to be looking at here is compressed liquid, right? Compressed liquid is going to be the region to the left of the saturation curve. So again, here is for example, a TV diagram. Here's a saturation curve. This area here is compressed liquid. This area that I'm drawing here that we just looked at was saturated vapor. So we're looking here now at a saturated liquid, compressed liquid. So compressed liquid. The table is not used that often, but we will be using it. It's table A7. Okay. So again, like in the superheated vapor region, in the compressed liquid region, pressure and temperature are independent of each other. Compressed liquid is characterized by these following situations. If at a given temperature, if my pressure is greater than saturation, I'm in a compressed liquid. If at a given pressure, my temperature is less than saturation, I am a compressed liquid, right? The example of water boiling at 100 degrees Celsius at 1 atmosphere. If my temperature of the water is below 100 degrees Celsius, I am therefore a compressed liquid. And then also for all these other states or all these other given situations where at a given pressure, temperature, if my specific volume is less than, this is a typo, this should be the specific volume of a fluid. If my specific volume is less than the specific volume of a saturated fluid, therefore I am compressed. If my internal energy is less than that of the internal energy of a saturated fluid, I am compressed. If in my enthalpy is less than the enthalpy of a saturated liquid, then I am a compressed liquid. Now, you'll notice that for the compressed liquid tables, when you go ahead and look at the varying pressures, like if you go back and look at the saturation or the superheated vapor tables, you see that you have sections of the table for varying pressures, right? So you have a pressure, then you have varying temperatures, and it gives you the properties. And for another pressure, you have varying temperatures and the properties. It's the same thing for the compressed liquid table, but you'll notice that the jumps in pressure are significant, right? It goes from low pressures to high pressures without much tabulated values for intermediate pressures. So it makes using the compressed liquid tables very impractical. So we're pretty much not going to be using it. So then the question comes is, well, how do we quantify properties for a compressed liquid? Right? In order to do that, we're going to make an approximation. Okay, we're going to make an approximation for compressed liquids. And here's the approximation. We're going to treat the compressed liquid as a saturated liquid at the given temperature. And the reasoning is when we look at properties, you're going to see that properties change more for varying temperature than they do for varying temperature at a given pressure. They vary more that way than they do for varying pressure at a given temperature. So the approximation is I am going to assume that my compressed liquid is a saturated liquid at the given temperature. And the reasoning again behind that is that properties depend on temperature much more strongly than they do pressure. Right? So a given property, Y, right, that can be internal energy, specific volume, or whatever. I'm going to look at the compressed liquid temperature at the saturated fluid as a saturated fluid. Or here's the notation that we'll be using. My specific volume, for example, of a compressed liquid is approximately equal to the same specific volume at a given temperature. All right, so what does that basically mean? That means that I can, for example, assume that let's go ahead and erase this and show you an example of what I mean. I can assume that my specific volume of a compressed liquid at any pressure at 20 degrees Celsius is going to be equal to this, right? I go ahead at 20 degrees, I look up what my specific volume is, right? And that's only for, that would be for a saturation temperature of 20 degrees and a saturation pressure of 2.3392. And I'm saying that the specific volume for a compressed liquid for any pressure, right? It could be 50 kPa, 100 kPa. It's still going to be 0.001002. All right, we'll come back to that with some more precise examples. Just as a note, we have we have all these reference points, right? We have values for these properties based on what's called a reference state or reference values, right? So values of internal energy, enthalpy, and entropy, they can't be directly measured, right? There's no like internal energy meter like there is like a thermometer, right? There's no enthalpy meter, there's no entropy meter. So thermodynamics, actually, we're not interested in the holistic values of these properties. We're interested in changes in these properties. So as a result, we choose a convenient reference state and assign it a value of 0. For example, water, the reference state is a saturated liquid at 0.01 degrees Celsius, where we attribute an internal energy and an entropy value of 0. Sometimes different tables use different reference states. So we must always use a consistent set of tables. So the only tables we're ever going to use in this class are the ones in the back of your book. Okay. So let's go ahead and compare this approximation. All right. So we went ahead and earlier in the slide prior to this one, we talked about this approximation for compressed liquids, right? And I get confused, and I understand that there's some confusion about it because, wait, you're telling me, Dr. Barty, I just go to table A7, but I can't really use table A7 because the variation in pressure is so great, it's hard to fixate on a value. So we have to use this approximation where I treat the compressed liquid as a saturated liquid at a given temperature, right? It's a lot of words and we tend to get confused and not sure how to apply it. So let's just do a small example here. All right, so I want you guys to find the specific volume of water at 40 degrees Celsius and 5 megapascals from table A7. Right, so go to your compressed liquid table, 5 megapascals happens to be a pressure that's tabulated there. So if we do that, here's an excerpt from table A7. Pressure, 5 megapascals. Great. Temperature, 40 degrees Celsius. What is the specific volume? Specific volume is 0.001057 meters cubed per kilogram. Great. Now, let's try that same thing using the approximation that we just went over. So now go to table A4, which is the temperature-based saturation table for water. Let's go down to 40 degrees, right? Assuming that remember, we're assuming that the compressed liquid at 40 degrees and 5 megapascals has the same specific volume as a saturated liquid at 40 degrees. So we go to the saturation table, we go down to 40 degrees, and we find that the specific volume is 0.001008 meters cubed per kilogram. So it's interesting. This actually, the real pressure associated with this value is 7.4 kPa. So you're telling me that water at 40 degrees Celsius and 8 kilopascals has the same specific volume as water at 40 degrees and 5,000 kilopascals, because 5 megapascals, right, is equal to 5,000 kilopascals. This pressure is like almost 1,000 times greater than this pressure, but the specific volume changed from 0.001005 to 0.00100057. So there was a small change in specific volume for a huge, incredible increase in pressure. So the whole assumption here is that properties change very little with pressure. So in order to be able to quantify my compressed liquid properties, I need to use the approximation because these compressed liquid water tables just have huge values for pressure that we're really not going to be going to very often. So instead, if we use the approximation that the property of the compressed liquid is the same as the property at the saturation liquid at the compressed liquid temperature, right? The compressed liquid temperature is 40 degrees Celsius. Therefore, I will assume the property of that compressed liquid is the same as a saturated liquid at 40 degrees Celsius. I hope that makes sense because this is the approximation that we are going to be using from now on. Okay, I hope that's clear. I just want to cover one other thing. What happens, for example, if we're looking at a property and it's not at an exact tabulated value, right? Let's say that here I have a temperature at 100 degrees and I have a temperature at 120 degrees, but maybe my temperature is 110.5 degrees. I have to do something called linear interpolation. I assume you've done this before in prior classes, linear interpolation. But basically, linear interpolation means that these values change linearly between iterations, right? So it's used when states encountered in solving a problem do not fall exactly on the grid values provided by the tables. So again, we just assume that the properties vary linearly between two known points. So let's say we have an x and y point, right? x1 is tabulated, y1 is tabulated, x2 is tabulated, y2 is tabulated, but I want to find y3 based on based on x3, right? We assume that the values between state point 1 and point 2 are linear, right? Linear being a line, mx plus b. So basically what happens is I have what's called a linear interpolation equation where a value y that lies between 1 and 2 is going to be based on a linear increment between 1 and 2, where x3 is given and y3 is I'm trying to find. For example, if I have a property that I'm trying to find based on another property, I can go ahead and look it up by linear interpolating. I hope that's clear. I assume you've done this in prior classes. If not, you can go ahead and try to practice this or contact me and I'll give you a more clear explanation if this is not clear to you. All right, I think this is a good point to stop this presentation.